So on Thursday, we left off working through lecture set number 6. And on lecture set number 6, we were currently working through exercise number 1, which was on slide 17. So we worked through part A of that exercise. So the first thing that we're going to do today is pick up with part B of the same exercise. And then we'll work through exercise number 2, and that'll bring us to the end of lecture set number 6. So that's the first goal for today, is finish this lecture set. After we finish the lecture set, I will take some time, maybe like 5 or 10 minutes or so, just to survey if there's any assignment questions, as the third assignment is due this evening. Following that, I will talk about the midterm. So there is already a question in the chat. How many questions will be on the midterm? There's going to be about 600 questions on the midterm. And so when I get to the midterm part, I'll go over the basics of how it's going to work. There was a student on Thursday that asked if I would talk about it today. So if there's any questions about it, I'll take those as well. And then I'll move on to lecture set number 7. Yeah, I said 600. It was just a joke. I don't know how many questions are on the midterm. I usually have usually I ask about 4 or 5 questions, more or less a question a unit, basically. And then the questions have parts associated with them. So it's not like 1, 2, 3, 4. It'll be like 1 A, B, C, D, 2 A, B, that kind of thing. So that's the I rewrite the midterm every year, so it just depends kind of like what I come up with and what I think is redundant and that kind of thing. So probably like somewhere in the area of 4 to 6 questions, let's say. But again, there will be parts associated with them. If you use the sample midterms that I posted online, that'll be a good guide. But like I said, I'll come back to talk about the midterm in a little bit. So we're going to finish lecture set 6 first, because that's the most important thing. Then we're going to talk about assignment number 3, because that and the lab quiz are due this evening. Then we'll talk about the midterm, because that's next week. And then we'll pick up with lecture set number 7, because that is the next set of material that we need. Okay. All right. So for lecture set 6, as I said before, we left off with question or part 1A. So in part 1A, what we were doing was finding the probability that we are within a particular amount of the population mean. And the purpose of this question is to illustrate that these types of probability calculations are actually the same as the probability calculations that we learned about for the normal distribution. So what I mean is the process that we are going through is effectively identify the probability statement that you have, or the quantity that you're interested in. Given your limits, convert to a Z-score. So that's what we are doing here. Now, when we're working around a mean, our conversion to a Z-score requires standardization in a slightly different way. So you'll notice that the formula shown here we have X bar minus mu over sigma divided by the square root of n. Effectively, you can think of it as a second Z-score formula. So we have 2 Z-score formulas. We have X minus mu over sigma. And now we have X bar minus mu over sigma divided by the square root of n. So in terms of keeping them straight, when we want to standardize a single value X, we subtract mu and divide by sigma. When we want to standardize a sample mean, X bar, we subtract mu and divide by sigma over the square root of n. Once we have the z-score, the process is exactly the same. So we would go to our standard normal table, we would look up the bounds, and then based off of what the quantity is, we would, subtract from 1 or take the value directly, or subtract the smaller bound from the lower bound. It just depends on what we're looking for. But the only difference when we're talking about a sample mean is how we standardize. All right, so in part B of exercise number 1, we're asked, what is the probability that X bar is less than 0.29 milligrams per centimeter cubed for all samples with n equals 5? Okay, so in part B, we actually have a very direct question that is specifying almost explicitly what the probability is that we are looking for. Okay, I'm going to just flip over to a separate page because I ran out of room on this one. All right, so we are here now. So we want to know the probability X bar is less than 0.29. Okay. So in this case, we can do this in a couple of ways. Again, we can standardize first and then apply the standardization and then apply the z-score into the formula directly. Or we can write the entire expression as, what is the probability that z is less than 0.29 minus 0.3 divided by 0.06 over the square root of 5. And then just as a reminder, all that's happening here is inside the expression, I am applying our z-score formula. Okay, so these two parts here, those are the same thing. I'm just writing it directly within the probability statement for, I guess, just for sort of to condense the solution. Okay, so then all we have to do is solve this. So now we have, what is the probability z is less than, and in this case, we will end up with negative 0.37. Okay, now, usually when we have this type of problem, again, the recommendation is to sketch. So if we were to sketch this, we could have started by sketching out the original problem, or we can sketch from the z-score. So let's say that we made a little sketch at the beginning of the problem. Okay, so here is mu, which is equal to 0.3. Okay. Here is our value, which is equal to 0.29. And we are looking for this part here. Underneath the curve. Okay. All right, now that we have this set up as a statement about a z-score, the only thing that we have left to do is go to our normal table. So I just need to pop those out here. Here's my negative table. Here's my positive table. Okay, so our z-score is negative 0.37. Okay. So that means that the probability that X bar is less than 0.29 is equal to 0.3557, because the probability that Z is less than negative 0.37 is 0.3557. Okay, so here we have, here we then end up with okay. So again, this one is a pretty straightforward problem. Just transformation, look the value up. Because we have a less than, it's a direct pull from the table. So there's a lot of nice things about this question that make it a bit quicker to work through. Any questions? Okay, so we have one more exercise for lecture set 6. Okay, so the way that the table works is you have Z scores that line the axes and you have probabilities that sit inside the table. In this question, we're being given, we calculated a Z score. So we want to know the probability that a Z score is less than negative 0.37. So negative 0.37 is a Z score, which means that it is a value that sits in the axes of the table. The probabilities are always the value that sit inside the table. So if you have a probability or an area under the curve, those are the same thing in this context, then you start inside the table and go out to the axes. If you are looking for a probability, then you start on the axes and go inside the table. That makes sense? Okay. Okay, so in exercise 2, it says, suppose the mean annual salary of classroom teachers is 55.4 thousand. Assume a standard, period here. Assume a standard deviation of 9.2 thousand. Okay, so we are being told in this question that the variable of interest is the annual salary of public classroom teachers. So this is the thing that we're measuring. We are told that the mean of the annual public salary is 55.4 thousand. Okay, so this implies that the population mean is 55.4 thousand. So we can leave this as 55.4 for the question, since our standard deviation is on the same scale. If you wanted to, you could also write it so you can also use 55,400. It doesn't matter which way you write it, as long as the standard as long as every variable or every value that you use is on the same scale. So we can keep it as 55.4, or we can write it directly as 55,400. It doesn't matter, as long as everything is on the same scale. Okay, and then we're told assume a standard deviation of 9.2 thousand. So that means that sigma is equal to 9.2. Okay, so we can also use sigma's 9,200. It says we can use either representation of the value as long as they're on the same scale. Okay, in part A, it says determine the sampling distribution of samples for size 15 or for size 15. Okay, so for the sampling distribution, we're going to talk about 3 things: the mean, the standard deviation, and the shape. Okay. Okay, so the mean is easy because the mean of the sampling distribution is equal to the true mean. So here we would just have mu x bar is equal to mu is equal to 55.4, right? So that one is easy to compute. It's always just equal to the population mean. The standard deviation is equal to sigma over the square root of n. So that's going to be 9.2 over the square root of 15, which is 0.613. Okay, now the shape. The shape is a bit tricky because we don't actually know what the shape of the original population is. We are only given samples of size 15. So from the central limit theorem, we know that we do not have enough information to say that X bar is going to be approximately normal, as the central limit theorem requires that we have at least 30 observations in order for X bar to return to normality. So without knowing the original shape, all we can say for sure is this would be similar to the original population shape. Okay. So I just have here, this would be similar to the original population shape. And what I mean is, for example, suppose that the population of interest, so the mean salary was right skewed, for example. At samples of size 15, the sampling distribution would still be right skewed. It wouldn't be as strongly right skewed as the original population, but it wouldn't be normal either because, again, the central limit theorem says that we need at least 30 observations for X bar to return to normality. Okay, so I'll come back to this point in a little bit and actually illustrate what this looks like, but the key point is that the shape will be similar to the original population because we do not have a large enough sample size for the central limit theorem to take over. Any questions? We don't. I was saying hypothetically, if the population was right skewed, then the sampling distribution here would also be right skewed. Okay. Part B, we have the same question, but we're increasing the sample size now. So we're going to have our three components: mean, standard deviation, and shape. So we have mu X bar is equal to mu, which again is going to be the same. So the mean is not affected by sample size. It's consistently at the same point, regardless of the sample size. Our standard deviation will be affected by sample size. So this is now over 50, the square root of 50, sorry. So that gives us 0.184. Okay, and now for the shape. Okay, sorry, one sec. Good catch. Okay. Thank you, Raleigh. Okay, so now for the shape. In this case, we have more than 30 observations. So we can say, since n is greater than 30, the shape will be approximately normally distributed according to the CLT, which is the central limit theorem, right? So in this situation, because we have exceeded the the rule or the rule of thumb of the central limit theorem, which again says that if your sample size is greater than or equal to 30, the sampling distribution of the sample mean will be approximately normal. In this case, because n is greater than 30, we can say that the sampling distribution will be approximately normal. And we're able to do this even though we don't actually know the original shape of the population. Okay. Well, the rule is n greater than or equal to 30, but 50 is bigger than 30. So since 50 is bigger than 30, it will be normally distributed. Cool. Okay, so just to give a visual of what's going on here, let's say again, so hypothetically, that the salaries are right skewed. Hypothetically, we don't know this, but just for example. Okay. So just as an illustration, this isn't, we don't know the shape, just for example. Okay, so we are going to consider 3 scenarios. Okay, so here we're going to have the population. Here we're going to have sampling distribution. For n equals 15. Okay, and then in the last plot, we'll have the sampling distribution for n is equal to 50. Okay, so we're going to put the mean in the center of each of these axes. All right. So the population is going to look something like this, right? So we clearly have, let's say hypothetically, we have this right skewed distribution. When n is equal to 15, what's going to happen is it's going to move a little bit towards the symmetric shape, but it's still going to be right skewed. So this one might look a little bit more like this, for example. So you can see that you still have this right skewness, but it's not as strong as it was in the original population. And then in the last case, I need to make sure my mean is in the middle here. We're going to get something that is approximately normal. Okay. And that's basically what the central limit theorem is telling us, is that if you start from the population of any shape, so let's say a right skewed shape, as we collect larger samples, the distribution basically returns to normality. So you get this flow back to normal in terms of the sampling distribution of the sample mean. Okay. Okay, so empirically, it could be the case that it is still slightly right skewed. Like my guess is that the reason you're asking this question is because you're looking at the histograms on the assignment and they're not like perfectly normal and they have a very slight skewness to them. I don't think that given that empirical histogram, you would be wrong in making that conclusion, but based off of the central limit theorem, we can say that that is approximately normal. So I guess you have a little bit of wiggle room in that sense. I suppose like what it comes down to is how strict you want to be. Okay, part C says, what is the probability that the sampling error made in estimating the population mean salary of all classroom teachers by the mean salary of a sample of 50 class of Rome teachers? I don't know what a class of Rome is. Of a sample of 50 class of Rome teachers will be at most 1,000. Okay, so this problem, part C, this is a particularly tricky problem because the wording, when you read it, it's kind of like what do you want from me exactly? But this question is actually exactly the same as part A from the previous illustration. So this is just asking us, what is the probability that for samples of size 50, our true mean value, or X bar rather, is going to be within $1,000 of the true mean. So basically all we're asking here is, what is the probability that mu minus 1,000 is less than X bar is less than mu plus 1,000? Okay, so this is going to be the probability of 54.4 less than X bar less than 56.4. Or you could write this as the probability that X bar is between 54,400 and 56,400. So we're just subtracting $1,000 from the mean in each. We're subtracting and adding $1,000 to the true mean, and then finding the probability of being within that amount. Okay, so visually, sorry about that. Maybe I'll just move this over here so I can sketch it below. All right, so visually, we would basically have the following. So here is our sampling distribution. Here is 55.4, which is the true mean. Here is 56.4. Here is 54.4. And this is what we're looking for. So we just want the area between these two limits. Okay, so all we have to do now is standardize our values. So we're going to have 54.4 minus 55.4 divided by 9.2 over the square root of 50 is less than X bar is less than 56.4 minus 55.4 over 9.2 divided by the square root of 50. So this is going to be the probability. And I'll just check these really quick to make sure I didn't. Okay, so this is going to be negative 0.77 is less than X bar is less than 0.77. Okay, and now all we have to do is go to our normal table. So this thing is going to be the probability. Oh, sorry. These are Z's now. Okay, so we have 0.7794. And then we have the negative value. Okay, so that's negatives. The probability of being less than negative 0.77 is 0.2206. Okay. And that gives us 0.5588. All right. Any questions? Okay, so in part D, it just asks, why are we able to do the calculation that we did in part C, but we could not do that when n is equal to 15? Okay, so when n equals 15, we do not know if the sampling distribution of so when n is equal to 15, we do not know if the sampling distribution of the sample mean is normal. Therefore, we can't use the normal table. Okay. So basically, the idea is the calculation that we did in part C, we're only allowed to do that because we know that when n is equal to 50, the sampling distribution is going to be approximately normal. When n is equal to 15, we don't know. In this case, we actually don't know what shape the sampling distribution is going to take on. It's going to probably be something closer to the population mean, or something in between the population shape and the normal shape, but it won't be quite normal. So therefore, we can't apply the calculation techniques that we used in part C, because that requires that we can assume normality about the variable. Any questions? I'm not seeing any. So that that brings us to the end of lecture set 6. Okay, so lecture set 6 was entirely devoted to basically the definition of the sampling distribution, the definition of sampling error, and the central limit theorem. So these are the key points that we took out of this lecture. We also have some probability calculations like the ones that we just saw, which are based off of the techniques we learned in lecture set 5. So assignment number 3, which is due at the end of today, is basically a lecture set 5, lecture set 6 hybrid assignment. So at this time, I'm just curious if anyone has any questions about assignment 2. And if you have very specific questions, I do have office hours today from 1 to 2:30. So you can also ask during that time, but I'm happy to spend about 5 minutes or so answering any questions if anyone has any, and then I'll talk about the midterm and then we'll start lecture set 7. Okay, so it doesn't ask, it's not asking for 2 conditions from the CLT. It's asking for 2 conditions in which the sampling distribution could be normal. So there are 2 ways that you can end up at a normal sampling distribution. One of those conditions would be the central limit theorem itself, which basically says if you start from any shape, you can arrive at a normally distributed sampling distribution if your sample size is greater than 30. But there's another situation where you can end up at a normally distributed sampling distribution, and it doesn't have anything to do with the CLT. And that's the other condition. Does that help? Raleigh. Yeah, that's a good question because again, there's a bit of subjectivity that comes into play here. I think in R, in R Commander, when you produce the normal probability plot, it will circle the potential outliers, and in the output from the function, so the console, it'll actually list the numbers that might be potential outliers. For the assignment, you wouldn't have to graph the box plot to do it, though I guess if you're using R Commander and you're comfortable, you could do that relatively quickly, and then you could compare across the 2. That would be a very complete and a very good answer. But as I recall, R Commander from the normal probability plot will list the values, though I might be confusing this with the box plot. Does that help? Okay. Yeah, let me know. I think it'll list them, and I think the ones that are circled, like when it circles and has a number on it, it's kind of saying like this is an outlier. And it should be fairly obvious because it'll be a point that's kind of far away from everything else. So that'll give you a little bit more of a insight into what R is trying to say. Jordan, what formula would you use for 3F? I would use the binomial probability formula. No. No, 8D is just is basically the same type of question that we just went through in lecture. It's just asking you the probability that the mean is going to be less than a particular value. So that's just a standard normal probability question. Part B 8F. Oh, 2F. I only see one F in part B, which is number 2. But it would be that one because it's the same question, right? You just have to do it in R that time. Any other questions? Yeah, that's a good question. You can, okay, so when you're pulling a value out of the standard normal table, you can leave it as 4 and it'll be fine. If you round it to 3, it'll also be fine, but you can, in that situation, you can leave it. I realize that this is a bit annoying because there's the decimal place thing, but you won't get dock marks if you just take the number directly out of the normal table. Okay. All right. So, all right. So midterm notes. Okay, so this is the first page of lecture set 7. So, in terms of the midterms, term tests, I will post after lecture today, not right after lecture, but before the end of today, I will post like an announcement about how the midterm is going to work, and all of the details that I think will be required to understand how the midterm is going to work. But in short, we're gonna, so there's 2 sections in the class, ASO1 and ASO3. So you will write the midterm during the actual lecture section for that class. So for example, okay, so ASO1 students, their lecture time is Thursday from 8 to 9:20. So that means that ASO3 students, write that down. It's Thursday, November 4, 8 to 9:20. And then ASO3 is Tuesday, November 2 from 8 to 9:20. But again, I'm gonna like resend a message with this stuff later. So those are when the 2 midterms are going to be held. The midterm is going to be run through CrowdMark. So basically what's going to happen is, like 5 minutes before 8 a.m., you'll get a link via email that'll say access the midterm by clicking here. And then you'll follow the CrowdMark link. And then the page will show you the questions and you'll have the hour and 20 minutes to complete the questions. And this will be the same thing as an assignment in the sense that you'll write it at home or at school, wherever you are, as long as you're by yourself. And you'll write your answers on a piece of paper, or you can write them on a tablet, or you can type them the same way you've been doing the assignments. And then you'll just submit the image into the CrowdMark box. Okay, so that's the same procedure that we've been using for the assignments. The only difference is the time limit. And anyone that has accommodation will have an adjusted time limit. The midterm is going to cover lecture set 1 through 6. Okay, so it's going to cover lecture set 1 through 6, which is assignment 1 to 3. So everything that we finished up at the end, or everything that we finished today, will be on the midterm. So lecture set 7 onward, that's not on the midterm. Once I know, like once I complete the test, I'll tell you how many questions there are. Like I said before, it's approximately, let's say 4 to 6 questions plus, like 5 multiple choice. It'll be something like that. So there's going to be a little set of multiple choice questions, and then there's going to be 4 to 6 written questions that would be the same style as what's on the sample test or what's on the practice problems. Yeah, I mean, like those are the basically the facts. Oh yeah, it's only lecture material. Okay, so the lab stuff is not covered. I can't write. Okay, so that just means you don't have to use R Commander on the midterm. The R Commander stuff only gets tested through the lab, so the lab quizzes and the lab final. No, I write the midterm such that it's impossible to finish it in 80 minutes. Just kind of a dick like that. Of course, it's doable in the time. Yeah, I mean, that's pretty much it. Like it's, if you go through the samples and you go through the practice problems and you're very comfortable with that stuff, I think you'll be fine. It's an open book test, obviously, because of the circumstances under which we're writing. You can't, okay, so things that you can't do are work with other people. You can't use a tutor during the test. You can't use any sort of, don't use anything that's external to the lecture, basically. You can use your lecture notes. You can use the assignments if you want. That's fine. I mean, anything that's on the course website is allowed, basically. That's the definition of open book in this context. No, I'm not trying to give you heart attacks. I don't know. Students always ask how many questions are on the test, and I just don't know why it matters. Like, I never really understood why it matters, I guess. Because the test is 8 to 9:20. I would never give you a test where it's like, this is an hour and 20 minutes, but the test is 6 hours to complete. Like, that's ludicrous. Like, I would never do that. No, there is a style of testing where I've only written this twice. And the way it works is the test can't be finished in the time frame, but you don't grade out of the total on the test. You grade based off the highest score. So that there is a style of testing that's like that, but I'm not doing that. It's a test that you can finish if you know the material. Hold on. What is the probability of a randomly selected student getting at most 110 on the midterm? 0, because there's no bonus questions, and the shape would be extremely left skewed if that was possible. You don't know how long the homework takes me, maybe 6 questions. Yeah, but homework is longer by construction. It's not an assignment. It's a different thing. Oh yeah, I thought of this really weird. This is a stupid question, but I'm gonna ask anyways. This is more for like a generational information. Do you guys know who the Backstreet Boys are? Okay. No, it's not. I would have expected people to say no, because that's from my childhood, essentially. You guys wouldn't have been born. So, okay. I guess they transcend time. So then I guess like Spice Girls, NSYNC, 98, like all these like pop bands are known. Yeah. Okay, I'm surprised. These are the kind of questions that are really of interest. I am aware of who the Jonas Brothers are, though I've never like I know them because of the move, like the one Jonas Brothers in Jumanji, which is a good movie. Well, some of the students in here are probably like 18, 19 years old. So that's, you know, almost a 20-year difference. Well, not 20. Oh, about 15 years. I'm 35. So favorite band? Probably Rush. Attaboy Kareem. Don't find out. It's better that way. Okay, I I digress. I'm really glad all of it. I'm gonna timestamp that as very important question. So anyone that wasn't here clicks that first, and then they're like, what the hell is this nonsense? It wasn't as good as the first one, but it was entertaining. Okay, any other questions about the midterm or the assignment? Or I guess the lab quiz, because that's also due this week. Those are the three most important things. The average for the midterms, that's a good question. I'm gonna say it's in like the area, it's like a low 70 on average, but there's a difference pre versus post COVID. It's usually a little lower in class than it is online. But yeah, like let's say like high 60, low 70s on average. Oh, there's one other thing I just remembered too. Lab quiz due Thursday, right? I thought, no, the lab quiz is not due tonight. It's just due this week. The assignment is due tonight and the lab quiz is due October 28th. So that would be Thursday. Yeah, I have it on a Thursday in the lecture outline. So unless the lab coordinator updated that, but I think that this is still correct. Okay, cool. Okay, yeah, one other thing. So because of the structure of the lectures and because the term tests are getting written on 2 different days, there will be a lecture video that I will record for whatever we need to finish lecture set 7, essentially. So you'll be responsible for watching that on the other day. So you can watch it whenever you want, obviously, but there will be a lecture recording next week that you're responsible to get through so that when we come back from break, we can keep moving forward with the material rather than just picking up from where we left off before the break. Okay, so I'll post another video essentially like on the weekend or something like that, and you'll have to watch that before, because during the tests themselves, I will be in the lecture. I'll be in the lecture room, but that will be to take questions from students writing the test, if there are any. So that anyone that isn't writing, you'll have that video to watch. So you're not completely removed for the week. Okay, I think that's pretty much it. So sorry, any other questions about midterms or whatnot? It's okay, like let's say that you write the test on the Tuesday, then on Thursday watch the video. If you write the test on the Thursday, then on Tuesday watch the video, is basically what I'm saying. But yeah, I guess that would mean there is no formal lecture next Tuesday, Thursday, but there will be lecture material. Yeah, we'll do one for the week. It might be a little bit longer depending on what I need to do, but there'll be one, yeah. Okay, so let's get into this next set, because the more we can push through now, the better, because the assignments aren't going to stop. So we're going to start lectures at 7. So for the last like 20 minutes or so, we'll work through this. Lecture set number 7 is the first lecture set where we're actually going to be talking about statistical inference. So we are officially starting the second half of the course with starting lecture set number 7. So the second half of the course is entirely devoted to actually making statements. Yeah, perfect. I'm also going to send a confirmation email about that to the students as well, but that's a good point. Oh, sorry. And then for people watching, the point was like your My Student system will show you when your exam date is, because it shows you when your lecture time is. Anyways, okay, so the second half of the course, lecture set 7 to the finish, is devoted to statistical inference, which means that what we're going to be interested in doing is actually using samples to make statements about population values. So we're basically going to be learning about a number of different techniques that we can use to make a statement about some population quantity. The first technique is called a confidence interval. So lecture set number 7 is devoted to the construction of confidence intervals, and we're going to learn about them in 2 different ways. Okay, so first off, every confidence interval is built around a point estimate. So the confidence interval is basically is 2 numbers, and these 2 numbers are found by constructing bounds around what is called a point estimate. A point estimate is simply a value that would, well, estimate some population quantity of interest. For the most part in this course, we are focused on estimating the population mean. That will be in almost every situation that we look at for the next few weeks, the value that we are interested in making a statement about. So to estimate the population mean, we need to build a reasonable point estimate. Our point estimate for the population mean will typically be X bar, so the sample mean. Technically, every population quantity has a point estimate that could be used to estimate it. So X bar is a point estimate of mu, which is the population mean. Little s is a point estimate of sigma. So the sample standard deviation is a point estimate of the population standard deviation. The sample variance is a point estimate of the population variance. So basically, given a sample of information, we can construct a value that estimates a population quantity. And that's what a point estimate is. Okay. So for example, suppose that these 10 values here were a sample. So this is a sample from some population with mean mu. Okay, so these 10 values are a sample taken from a population. The population has mean mu. Compute a point estimate for mu. Okay, so a point estimate for mu is X bar. X bar equals the sum from I equals 1 to n of xi divided by little n. So this is the sum from I equals 1 to 10 of xi divided by little n. So this is 1083 over 10. So that's 108.3. Okay. So X bar equals 108.3. That's a point estimate for mu based off of this sample. Okay, so again, for any point estimate, we can build a confidence interval. The reason that we build confidence intervals is because the estimate on its own doesn't really give us a lot of insight into where the population mean could actually be located. So we know that the smaller the sample we collect, the bigger the sampling error we will expect. So the more information we have, the better. What the confidence interval does is it basically gives us a range. So it gives us two numbers that would contain the population mean. And effectively, for the same confidence level, the more information you have, the closer those two numbers will be to one another. And the less information you have, the further those two numbers will be from one another. So essentially, the interval is going to be wider for less information, and the interval is going to be narrower for more information. But what the confidence interval is doing is it's basically accounting for the sampling error. The construction of the interval is actually very straightforward. So it's a three-step procedure, which I'm going to outline in a couple of slides. And all we need to do is compute the point estimate, find a z-score. So you're going to see that z-score notation again here. So we're continuing to use that same definition from lecture set 5. And then we're basically just adding and subtracting two values with a bit of multiplication. So it's not a very tedious process to build the interval. So the most general definition of a confidence interval is given in equation 1. So it's basically a point estimate. So for example, X bar plus or minus what we call the margin of error. And this part here, the margin of error, this changes depending on problem and requirements. So depending on like what kind of confidence interval you want to build and what value you want to estimate, the margin of error is going to change. For this lecture, we're always going to be building confidence intervals for mu, with the exception of the very last unit where we talk about regression, but we'll get to that later. But for the most part, we're always going to be building confidence intervals around mu. So the point estimate is always going to be X bar or maybe 2 X bars, depending on if we're doing a difference or not, but we'll get back to that later as well. So the thing that we're going to be calculating most often and having to account for is the margin of error. So that's the part of the formula that can change depending on confidence level and sample size. And we're going to see lots of illustrations of this in a little bit, but every interval basically has this general form. So we have a point estimate, and then we just add and subtract what we call the margin of error to that point estimate. And then in the end, we get an interval that looks like this here. So we have our point estimate minus the margin of error and our point estimate plus the margin of error. And that's a confidence interval. It's literally just those two numbers, and it's telling us where we think the true mean might belong. Okay, so for any confidence interval, we will specify the confidence level. So the questions will usually say, we want to compute a 90% confidence interval, or we want to compute a 95% confidence interval. This will be given to you in the problem. So with that being said, our construction of the interval boils down to taking that confidence level and finding the z-score that would work with that confidence level. And then we use that to compute the margin of error and then add and subtract that to the mean. We also have an interpretation of the interval. This is going to be part of the construction process, where depending on the confidence level, we basically have this generic statement where we say we are some percent confident that the population mean is between the lower bound and the upper bound. So that would be the most generic interpretation of the confidence interval. We are, for example, 95% confident that mu is between this number and this number. That's how we interpret the interval. The important parts of this are, one, we have the right confidence level. So in our interpretation, we don't want to say like we're 90% confident when we use the 95% interval, for example. We also want to make sure that we consistently use the word confident. I'm going to talk about why that's the case momentarily. But when we are working with confidence intervals, they are giving us a percent confidence, not a percent accuracy or a percent determination, right? So we can never say something like, we are 95% sure that the population mean is between this and this, because that would be incorrect based off of how the intervals work. It's always giving us a degree of confidence about where mu would sit, given the sample that we're working with. All right, so why is this the case? Well, first, recall that for any population, we can collect as many samples as we want. So we can sample over, well, for any infinite size population, we can sample over and over and over and over again. So we can continue to collect as many samples as we want for a given problem. There is always the possibility that some number of those samples are bad samples. So they're misinformative samples, which would mean that the confidence interval that's built from that sample might not actually contain the true mean. So the way that our interpretation works for the confidence interval is based off the idea that if we were to repeatedly collect samples from the population, so we sample over and over and over again, and let's say we have 1,000 samples. If we build a confidence interval for every sample, so now we have, say, 1,000 confidence intervals, then if they're all 95% intervals, we would expect that 95% of the 1,000 intervals actually contains the true mean, which would mean that 50 of the confidence intervals do not contain the true mean. So this is why we use the word confident rather than sure, because for the individual sample, we have no idea if the sample is actually going to contain the true mean or if it's going to miss the true mean. But we know that if we were to repeatedly collect samples of the same size, 95% of the time, the confidence intervals for each sample should contain the true mean. So this interpretation is based off the idea that we can repeatedly sample, but for the one individual interval that we're computing, we don't know if it actually does or does not contain mu. Okay, so to better illustrate that point, I have a visualization here. So this bar here down the middle is going to be mu. Okay, so this vertical bar, this is the population mean. Each one of these here is a confidence interval. So let's say that this is 95% confidence interval number 1. This is 95% confidence interval number 2. This is 95% confidence interval number 3. This is 95% confidence interval number 4. And this is going to be 95% confidence interval number 5. Okay, so suppose we collected 20 samples of the same size from this population. Okay, so we have some population that we're studying. We've collected 20 samples. And then for each sample, we built a confidence interval. Okay, so then for each, and then, so now we have 20 confidence intervals. Since they are 95% intervals, we expect that 95% of the 20 intervals are going to contain the true mean. Okay, so we expect 95% of the 20 confidence intervals will contain mu, right? And that's what this illustration is showing us. So you can see, for example, confidence interval 1, this captures mu because mu sits within the interval. Confidence interval 2, this captures mu because mu sits within the interval. Confidence interval 3, this captures mu because mu sits within the interval. Confidence interval 4, this one misses mu. So this one, you can see the horizontal, or mu, the vertical bar, is not within that horizontal line. And then confidence interval 5, it catches it, and the rest of them catch. So this illustration is basically showing us that across repeated samples, we expect that 95% of the samples that we collected will produce an interval that contains the population mean. And the problem is that we don't know when we only have one. Well, the problem is because mu is typically unknown, we don't know which one is actually going to hit the mean and which one is going to miss. So that's why for each individual interval, we can only say that we are some percent confident because we are interpreting the interval based on the idea that we are going to repeatedly sample from the population. Okay, and to be honest, like this is I think the trickiest part of the whole process is just understanding this interpretation. And it takes some time to get comfortable with this idea because you have to be comfortable with the idea that you can repeatedly sample from the population. And then you have to be comfortable with the idea that, okay, I have all of these samples in front of me. Each one of them is going to give me an interval. I don't know which one is going to capture mu, but I know that some percent of them will. And that's where the whole interpretation idea comes from in the case of a confidence interval. Right. Okay. All right. Any questions? All right. So let's suppose that for one of the samples on slide, so for the sample on slide 4, let's suppose that the 95% CI has the following form. So it's X bar plus or minus the margin of error. Okay, so the first thing it says is find and interpret this interval. Okay, so the interval is just going to be X bar minus the margin of error to X bar plus the margin of error. So that's going to be 108.3 minus 12.396 to 108.3 plus 12.396, which is going to be a number. 95.904 to 120.696. All right. And then we can say we are 95% confident that mu is between 95.904 and 120.696. So this would be a very simple illustration of confidence interval construction. What we're going to learn how to do next time is actually compute this quantity here. So once we learn how to compute the margin of error, we can do this just by starting from the sample directly. But this interpretation, this is the general interpretation for any confidence interval. So this is going to be consistent across all the problems that we see in this unit. The only difference is that we'll start to tailor the interpretation depending on what we're actually measuring. And we'll see lots of examples of that later as well. Okay, so suppose K equals 1,000 samples are collected and a 95% confidence interval is found for each sample. How many intervals should contain mu? We expect 0.95 times 1,000 equals 950 of the confidence intervals to contain mu. Okay. All right. Any questions? Any other questions? All right, so I'll stop there for today. On Thursday, we'll learn how to build the interval, and hopefully we'll have time to go through the t distribution and how to build in that distribution as well. But given the speed at which I work, I think we'll finish the first set of examples and then probably study the t distribution. All right, so I'll talk to you guys on Thursday. I'll post updates about the midterm later today, and I have office hours at 1 o'clock if anyone has any questions. And yeah, assignment 2 is due tonight, lab quizzes due Thursday, midterms next week, and then reading week. So have a good couple days, and I'll talk to you guys on Thursday.